Actually, you know, I changed my mind. Let's do the homework first. So, is there anyone that have questions they want to go over?
Number 10, the second part.
Okay. 8.2, just series. Scroll down to number 10. All right, got it. So here's number 10. Hopefully yours is similar enough. Okay, so this one says determine if the geometric series is convergent or divergent. How far did you get with this one?
I was able to figure out that it was convergent, but then when I was trying to find out the sum, I got stuck, like when I was breaking the things apart.
Okay, how did you figure out it was convergent? Or did you just like, it's 50-50? Yeah.
No, so when I broke it apart into like sigma 1 over 9 to the power of n plus summation sigma, a summation.
Well, it's also called sigma too,
Oh,
actually.
okay.
So yeah.
Okay, so summation of 7 over 9 to the power of n. And since both of them, those parts are convergent, I was able to say that it's convergent. That's how I.
Okay, so yeah, this one's the same. It's just they have a 5 to the n. So you said it was summation of 1 over 9 to the n plus summation. Well, I'll just use 5 because this question uses 5. 5 to the n, 9 to the n. So you have this, right?
Yeah, and then I did
Okay.
limits of both.
All right. Well, the one on the right is you can write it as 5 over 9 to the n, right?
Yeah.
So then this is in the form of is in the form of geometric series?
Yeah, it's in the form.
Okay. Let me just double check. So the index here is 1. And then goes to infinity. Actually, this is not quite in the form yet. So whenever you have an index that starts at 1, you want to change the exponent to be n minus 1. So this is actually not in the form yet. So I would probably just do a index shift. So if I change it to 0, then it would be to the power of, so I subtracted the index by 1, which means I have to add 1 to the exponent. Is that okay?
Yeah.
Okay. And then when the index starts at 0, we just want to have an n as the exponent. So let me just split this up. This is 0 to infinity. And then this would be 5 over 9 to the nth power times 5 over 9 to the first power, right?
Oh, yeah. I see.
And then I can just consider this as like the coefficient in the front. So that would be like your A.
Hmm.
So now it's in the form. So the sum of this series is a, which is 5 over 9 over 1 minus r. So 1 minus 5 over 9. So this would give you the sum of the series. Then this one, I think, is probably a similar process. So n equals 1 to infinity. Again, this is not in the form because when n equals 1 and the exponent is n, like that's not matching. So you have to change it. So, well, when we have just a number 1 is the same as 1 over n, right? Because 1 to any power is still 1.
Okay.
And then once you have it like this, you can write it as 1 over 9th to the n. Now we do the same thing as before. So we index shift it. So if we start at 0, if we move the index down, then we have to move n up by 1. So like that. And then you can see that 1 over 9 is your a and your r is also 1 over 9. So the sum of this series is a over 1 minus r. So here's your two sums, and then you would add those together to get your answer. Okay. Hopefully that's 11 over 8 for this question.
Yeah, that helps.
Okay, yeah, so I don't know if from this work you can identify like what mistake you made when you were working on it, but okay.
I found it.
All right.
Thank you.
Mm-hmm. All right, any other questions? Twelve. Okay, so here's 12. So this one says determine whether the geometric series is convergent or divergent. Okay, so first you can split it into two series because that's one of the properties of summation. So we have summation as n equals 1 to infinity of 0.9 to the n minus 1 minus the other summation, 0.2 to the n. Okay, hopefully you got that part. Do you know where to go from here or no? All right, so you want to get both of them in the form of a geometric series. So let me just get those for reference. All right, so here's the two forms. You want to get in one of those two forms. Because once you get in one of those two forms, you can say the sum is a over 1 minus r. So the first series, is it in the form yet? Is it in one of those two forms? Can you tell? Yeah, right. So this one is already in the form of this one right here. So therefore, we can already identify what the sum would be. So the sum would be a over 1 minus r. So a, which is basically the number here, it's a 1. So it's a over 1 minus r. R is 0.9 here. Okay, so that's the first series done. And then let's do this series now. So is this series in one of the two forms? Right, yeah, so this one is not in one of the two forms yet because the index starts at 1, which means it looks like this. But then you need the exponent to be n minus 1. So you have a couple of options here. You can either just like manipulate it with algebra to get it to be n minus 1, or you can just do an index shift. So I don't know what you want to do here. I guess we'll just do an index shift. So if we rewrite it with an index of 0, then we have to add 1 to the exponent. And then 0.2 to the power of n plus 1 is basically 0.2 to the power of n plus 0.2 to the power of 1. Okay? And this can be rewritten in the form 0.2 times 0.2 to the power of n. So now you can see that it's actually in this form, which means you can now write what the sum would be, which is a over 1 minus r, which is common ratio. Okay, so your final answer would be this sum and this sum. Well, these are subtracting, so this sum minus this sum. Okay, and that should give you 39 over 4. Yeah, no problem. All right, any other questions? Okay, in that case, let's just finish up 8.2 and then we'll start 8.3. Beatrice, did you find someone to send you the recording or no? Okay, all right. So this was the last thing we talked about, these three examples. So the next one is a special case of series. So we talked about, I don't even remember what series we talked about. Oh yeah, geometric series. So obviously not all series are going to be geometric series, right? That's a very specific type of series. So now we're going to learn about some other series that are not geometric series. So this one right here is one example. Let's see if we could figure out whether this series converges or diverges. Okay, so looking at this function here, 1 over n squared plus 3n plus 2. Why don't we just write down maybe, I don't know, like the first couple of terms to see what this series looks like. So the first number is when n is 0, which gives you 1 over 2. And then the next number is when n is 1, so that gives you 1 plus 3 plus 2, 1 over 6. The next number is 4 plus 6, so 1 over 12. Okay, so that's what this series, actually no, this is a series, so there's supposed to be plus signs in between them. So this is actually wrong. It's 1 half plus 1/6 plus 1 over 12 plus so on. Okay, now, does anyone have any ideas, just by looking at it, any ideas on how to maybe reach a conclusion to whether it converges or diverges? So at first glance, I don't expect you guys to see how you'd figure this out because it's not obvious at all. So the hint would be to look at the denominator and think about what you can do in a denominator, which may or may not lead you to figuring out what you need to do. But I'm gonna give you guys a couple more seconds to think about it. Okay, so now I'm gonna tell you the answer. You guys are not gonna like this, but you're gonna need to do partial fractions. So if we could split this into two fractions, how would you factor the denominator?
N plus 2, n plus 1.
N plus 2, n plus 1, yeah. Okay, and then the numerators, we don't know what they are yet, so we'll just leave them as a and b. So using our knowledge of partial fractions, which we went over before, you can find what a and b are. So I actually have the work right here. I did it beforehand. So we're gonna skip that part and I'll just write down what a and b are. Okay, so it turns out to be 1 and 1. All right, that's simple enough. So what we just did is we rewrote the series. Yeah, that's all we did, using partial fractions. So now once you have this rewritten version, what you can do is you can actually write the terms of the series again. So I'll write it down here. So this series is going to be, the first term of the series is when n equals 0. So that gives you 1 half plus 1 over 1. Actually, hold on, I got my a and b wrong. B was actually negative 1. So this was it. Okay, so that's your first term in the series. Let me just make sure I have everything correct, because I feel like I probably made a mistake somewhere. Yep, I'm sorry. A was negative 1, B was positive 1. So it's actually negative here, and positive here. Sorry about that, guys. So this is actually negative 1/2 plus 1. Okay, so that's the first term in your series, which should make sense because we already knew the first term in our series is 1/2 because we just listed it before. So negative 1/2 plus 1 is actually positive 1/2. So yeah, this is the first term in your series. Let's write down the second term in our series. So the second term is when n equals 1. So that would be negative 1 over 3 plus 1/2. Okay, let's write down the next term in our series. So that would be when n is 2. So that's negative 1 over 4 plus 1/3. Okay, so this is going to go on and on, right? As n gets larger and larger. What I'm going to right now do is I'm going to write down the nth term. So what would be the nth term? So this would be negative 1 over. Do you guys think you can write down the nth term?
Wouldn't it be n? And then plus 1 over n minus 1?
Say that one more time.
Wouldn't it be negative 1 over n plus 1 over n minus 1?
1 over n minus 1. Yes, that is correct. So that would be the nth term. And then can you go to the next term after that? So the n plus 1 term.
Negative 1 over n plus 1 plus 1 over n.
Yes. Okay. So this is generally how the series looks like. We basically listed out every single term. Now the question is there a way to simplify this? Because this is just a bunch of terms. Do you guys see any terms that cancel out maybe?
The negative 1/2 and positive negative 1/2, negative 1/3 and positive 1/3. So those things could cancel out.
Yes, okay. So this goes away with this, and then this goes away with this. And then technically the negative 1/4 should go away, right? It's just we didn't list out all the terms. So that goes away. And then these two last terms that we listed here, something goes away, right?
1 over n goes away.
Yeah, 1 over n with this 1 over n. Anything else? So if you're noticing what's happening here, the two outer terms are going away. So this is like the left side of the parentheses cancel out with the right side of the parentheses for the next term, and then so on and so on. So what that means is this term right here should have canceled out with whatever this term was over here. So that, in theory, should go away, right? And then what we're left with is basically, I mean, you could go on forever, but let's just see what the remaining terms are right now. So the only remaining terms are the 1. Let me change back the color. This term right here and this term right here. So right now we have 1 over 1 minus 1 over n plus 2, right? So this is what our series comes down to. And then if you guys remember what I told you about like evaluating an infinite series, you can just take the limit as n approaches infinity. So as the limit of n goes to infinity, what happens here?
It approaches 1.
Yeah, because this goes to 0, right? So that means this series here converges to 1. Okay. So this is a special case series. It has a special name. It's called the telescoping series. I don't know if you can find the reference. Where does n start at? N starts at 0 and goes to infinity. So Devin, this is the term when n equals 0, this is the term when n equals 1, and this is the term when n equals 3, and so on and so on. Yeah. So this series converges to 1. Isn't it constantly decreasing by fractions? Um, yeah, it is. Why is there something weird? How's it converting to 1? Remember, this is a series and not a sequence. So you're adding all the fractions. So it's 1/2, like we wrote the terms up here. So it's 1/2 plus 1/6 plus 1/12 and so on and so on. Mm. Okay, so this is the telescoping series. It's telescoping because all the terms cancel out. And yeah, I don't think this is in your homework or anything, so don't worry too much about this. Okay, so next special case. This one, we're not going to spend any time at all on this. So this is the harmonic series, which is summation of 1 over n. So if you were just to write down the terms for this series, it's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on and so on. Turns out it's divergent, okay? We're not going to see why it's divergent because it's not important, but this is a divergent series. It's also called a harmonic series. I think it's a reference to music, which I know nothing about. But yeah, this is a harmonic series. There was a question on your homework about harmonic series that I took out because I felt like it wasn't important. But if you want to see what the homework question was, I have it down here. So it was 1/2 plus 1/4 plus 1/6, which is basically the harmonic series, but with the constant in the front. So yeah, that was divergence. Okay, so that's all we had for section 8.2. The exam is November 12th. All right. So if there's no further questions, then we'll start section 8.3, which is the last section for the exam. Okay. Can you record this part? Yeah, did I not give you permission for this? No, I did not. Okay. So 8.3 is called the integral test. What is the integral test? Well, we will find out right now. So the integral test is the following. It says that if you have a continuous positive and decreasing function. So let's just take a moment just to figure out what all those words mean. Who remembers what continuous means?
No holes.
No holes.
Approaches the same value from both sides.
Uh,
No sharp edges. I mean, sharp vertices.
a function could still be continuous with sharp edges. You don't pick up your pencil. Yeah, that's how they taught it to you, like colloquially. But
isn't it like approaching the same value from both sides? That's how you know it's continuous.
no, that's if it has a limit.
Whoops.
But continuous means that there's no breaks or jumps in the graph. So yeah, that was a terrible explanation too. I don't think we need to talk about the formal definition because it probably doesn't mean much. But I think, what does someone say? Don't pick up your pencil. Yeah, I think that's a good interpretation of it. So if you have to like lift up your writing utensil when you're drawing a graph, then it's not continuous. So basically, it's all connected, I guess. All right, and then the second word in the sentence is positive. So that is pretty obvious. Positive just means the graph is above the x-axis, so that's fine. Decreasing function. So what does that mean?
Negative slope. Where values are going down.
Yeah, negative slope is fine. So as you look at the graph from left to right, it goes down. So that's decreasing. So as long as those three conditions are filled, then you can do this test called the integral test. So what does this integral test say? It says if you have a function f of n such that every term in that function corresponds to every term in a series, then you can conclude the following. So if the integral of that function is convergent, then the series is convergent. And then number two says if the integral of that function is divergent, then the series is also divergent. So what does this mean for us? Basically what it means is if you have a series that you don't know if it's convergent or divergent, instead of solving the series, you can just solve the integral instead. So for some series, that might be a lot easier, okay? Oh, Devin, square root of, what is that? Absolute value of x is continuous. Yeah, it's continuous. So let's look at an example of how the integral test can be useful. So take a look at this series right here. So this series says summation of 1 over n ln of n. Now, if you recall all the series we've been looking at so far, should be obvious that we don't know how to do this yet. So the only things we know how to do are geometric series. We can use a divergence test, but I mean, that's only for very limited scenarios. this isn't a harmonic series, and this is not a telescoping series because you can't really factor the denominator or anything. So what can we do? But the answer is on the slide. We use the integral test. So let's do that. Okay, so here's the series. If we were to use the integral test, first thing you guys have to do is verify that the three conditions are satisfied. So if I was to write down this function here, f of x equals 1 over x ln of x, you would have to check that this function is one, continuous, two, it's positive, and three, it's what was the last one? It was decreasing. Okay. So the best way to check all those things is just to graph it. So let me pull up a graphing tool. Okay, so here's the graph of 1 over x ln of x. You can see that it does satisfy all those conditions. Well, you do have to consider the upper and lower bound too. So our series was going from n equals 2 to infinity. So let me just mark 2 to infinity. So anything above the anything to the right of the blue line is basically where you have to look at to make sure the three conditions are satisfied. So to the right of the blue line, it's continuous because there's no breaks. It's all above the x-axis and it's decreasing. So this satisfies the conditions for the integral test, which means we can go ahead and use the integral test. I mean, I don't know. Whenever you guys get a question in this homework, section 8.3, which is the integral test, if they ask you to like solve a series using the integral test, like most of the time you're not going to have to verify these conditions, because if it doesn't satisfy these three conditions, then like why would they even ask you the question, right? So when you're doing your homework, you can just go ahead and do the integral test. Anyways, so it would be integral from 2 to infinity of 1 over x ln of x dx. Is this something we know how to integrate? One over x times 1 over ln of x. Sure. Okay, I have rewritten the integral. So what can we do now? Differentiate by parts. I think there's a better option. What you think about was integration by parts. There's no fine derivative by parts. But yeah, no, we don't need to use integration by parts. There is a better option here. So notice the ln of x and notice the 1 over x. So there's a relationship between those two things.
You could do u sub.
Yeah. And what would u be?
Ln of x.
Yeah, because the derivative of ln of x is 1 over x. So that means we could rewrite this as 1 over u du, right? And then the integral of 1 over u is ln of u. And then we can plug u back in. So ln of x. Evaluating this from 2 to infinity. So this is technically an improper integral, right? Because the limit is infinity. So what we're supposed to do was we're supposed to let the upper limit be some variable t, and then say limit as t goes to infinity of ln of x. So then we get ln of t minus ln of 2. And then we're going to evaluate this as t goes to infinity. And what would that be? Can you guys see? So what happens when you take the natural log of a really large number? Yeah, so this would be infinity. This is just a constant, this ln of 2, so that doesn't really change the fact that this would be infinity. Okay, so that's your answer. The series is divergent. Okay, so the main idea of this is that you have a series, and if you were to convert it into an integral, and if it's something you know how to integrate, then chances are you can do easily the integral test. Okay, what do you guys think? Any comments? But the area under 1 over x ln of x looks really small. Really? Let me see. Yeah, I guess it does. Maybe it's still infinity because we're going to like all the way to positive infinity on the right side. But yeah, it is a bit weird because the area does look small. But then again, like so did 1 over x, which was, or 1 over x and 1 over x squared. Do you remember those two? 1 over x squared. So we said that this one's 1 over x. We knew this one was divergent, and then this one was convergent. But I mean, the areas look small for both of them, so yeah, it's really misleading. Can't really judge by the graph. All right, so you guys think you got the general idea of integral test? Okay, so why don't you guys try this one on your own? So this one is another series, and you can use the integral test here, okay? You guys can go ahead and just skip verifying the three conditions because if I'm going to give you a question, it probably verifies the three conditions. So go ahead and see if you can integrate this. I'll give you 5 minutes. All right. Did registration start yet for the next semester?
Yes.
Oh, it did. Okay. November 10th. All right. I'm just wondering because, well, actually, it doesn't matter for the math department anyways because math department is always late for everything. They never update the like the CUNY first info for the math department. Yeah, registration for winter should be open because it's almost winter. Those of you who are taking math 156, what major is that for? That's only for math major, right? Physics? Wait, so we have physics majors in here? Math 156, that's intro to proofs for math. Two. Okay, yeah, I didn't know that. The last time I checked the roster, no one was physics major, so I don't know. Should I have skipped that session on cal2 about like application to physics? Should I go back to that? Yeah, I guess they do proofs in physics. Adolescent math education. That was my major actually. And then 160, that is matrix algebra. I'm assuming that's for computer science. All right, how are you guys doing with the question?
Couldn't find the limit, so I guess it's divergence.
I don't know, could be. I didn't do it yet. All right, let's go over it. So assuming that all three conditions are met, we are able to do the integral test, which says we can do the integral of 0 to infinity of 2 over 3 plus 5x dx. So who wants to walk me through on how to integrate this?
You can take out the 2 right away.
Okay. All right, I have done what you have ordered. U sub for 3 plus 5x. All right, let's try that. So u is 3 plus 5x. So du is 5 dx. Okay, and then we want to write it all in terms of u. So I guess we could solve for dxu. So it's du over 5 is dx. So this is 2 integral. I'm going to omit the limits because now we're in terms of u. So this would be 1 over u. And then dx is du over 5. So I'll just write it like this, du over 5. Okay, so now we have 1 over u, and we need to integrate that. So that would be, what's the integral of 1 over u?
ln of u.
Yes. So we have ln of u. We'll just put u back in now. So that's 3 plus 5x. And then have the 2 over 5 in the front. So now it's integrated. We had to evaluate this from 0 to infinity. So this would be 2 over 5 ln of 3 plus 5. This is an improper integral, so we're supposed to use a variable. I'll just use t. And then this is limit as t goes to infinity. And then minus the other one. So 2 over 5 ln of 3 plus 5x. The other one, 0. Okay. So here is our expression. And then as t goes to infinity, what do we get? Yeah, so the first term goes to infinity. So this is divergent. Okay, so because this integral is divergent, by the integral test, we can say that our series is also divergent. Okay, this is divergent. All right, any questions on that? All right, so moving on then. Okay, so do you guys remember the comparison test? So if you don't remember, that's okay. We will remind you. So the comparison test was for integrals, right? So it said that if you're smaller than convergent, then you're also convergent. And if you're bigger than divergent, then you're also divergent. Okay, so that's the comparison test. It appears that the comparison test also applies to series. So yeah, let's just read it down here. So suppose we have two series. So A and B are your two series. And here we're saying that B is the bigger one and A is the smaller one. So it says if B is convergent, then A is also convergent. And if A is divergent, then B is also divergent. So it's basically the same thing as like the integral version, but they're just restating it for series. So the comparison test also applies to series. Yeah, and why is this useful? Because when you're doing the integral test, so you're turning series into integration, you can actually use the comparison test again. So uh, let's see what else they have to say. Oh, and do you guys remember this integral right here? So the integral of 1 over x to some power. So before we said that if the exponent was greater than 1, so if you have stuff like 1 over x squared or 1 over x to the third or something greater, then that integral was convergent because the area underneath the curve got smaller. And then if the exponent was smaller than 1, then it was divergent. It was divergence. Yeah, because the area got a little bigger. Okay, so this integral was used a lot in that chapter. And it appears that this integral also applies to series. So it says that if you have a series in this form, so summation of 1 over n to some power, depending on what that power is, it'll converge or diverge. And the rule is the same as the other version. So this also has a special name, this series. It's called the P series. I don't know if any of you guys have ever heard of that before. There was one student who took BC calculus here, right? Which is like cal2 for high school people. So I think in that class they tell you about this series, right?
Yeah.
Yeah. Okay. So yeah, it's called the P series because I don't know, the exponent is P. I have no idea. But let's see how you can use this. So look at this example here. Determine the following series converges or diverges. So this is summation of n squared plus 2 over n to the 4th plus 5. The key here is that you can actually use the comparison test, but in series form. So before we even start, does anyone have a guess as to whether the series converges or diverges? I'll give you guys a hint. Ignore the numbers.
Converges.
Diverges? Why do you say diverges?
I said converges because
Oh, you said converges? Okay, why do you say converges?
power of n is greater than 1.
Power of n is greater than 1. Which n are you talking about? The top one or the bottom one?
The bottom one.
Okay, so that has a power of 4, right?
And
So it's
ignore the numbers and simplify it out or something like that.
okay. So if you're just looking at the denominator, where the power is 4, then is that your reason for why it converges?
Yeah, kind of.
Okay. Let me see what other people are saying. Converge, diverge, diverge, converge. denominator exponent is greater than numerator. All right, let's see. All right, let me switch to the board here. So regarding the comment on like the denominator exponent and numerator exponent, remember that we have these two here. So 1 over x and 1 over x squared. This one is divergent, and this one is convergent. So I don't think you can use that argument, because in both of these examples, the exponent in the denominator is greater than the exponent in the numerator. So we need some other argument besides that.
But if that's the case, isn't the P series wrong or something like that?
P series? Well, why would it be wrong?
Because didn't that say like if the power of x is greater than 1, it must converge or something?
Yeah, but you need to get it in the form of a P series first. Like this is not in the form of a P series.
Oh yeah. Oh yeah. My bad. Yeah. Oh.
No, that's okay. So P series is for 1 over x to some power. Okay, let me see what students say. Multiply by that it converges. Okay, yeah. Yeah, we can definitely do that. Let's do what that student was saying. So you can just divide everything by the highest exponent. So if you do that, you're going to divide everything by n to the 4th. So this would be 1 over n squared plus 2 over n to the 4th over 1 plus 5 over n to the 4th. And then as n goes to infinity, this would just be 0. Yeah, so this is a good argument as to why it converges. So yeah, that's very good. There is a different method that I'm trying to get at. So does anyone see a way we can figure out that it converges through the comparison test?
You can compare it to 1 over n to the power of 4.
1 over n to the power 4, that one?
Yeah.
Okay, and then what would be your inequality sign?
Less than?
Less than. Why would it be less than?
Because the denominator is smaller.
The denominator is smaller.
I mean, actually, no, it's larger. Whoops. Because it's larger.
Yeah. Yeah, so the denominator was n plus 5. So it's larger. Well, I mean, you stripped out a lot of terms with this 1 over n to the 4th. So maybe we can just go one term at a time. So instead of doing 1 over n to the 4th, let's do something else. Let's do n squared over n to the 4th plus 5. So that's all I did was strip out the 2. And then if we have this, what's your inequality?
Greater than?
Yeah.
Because the numerator is greater.
Yeah, so this would be greater than. We already know it's convergent, right? So, because we did analysis. So if it's convergent, uh, then we should probably get a less than sign, because if we're less than a convergent series, we're also convergent. So this makes us have a greater than sign. So what if we did, what if we, instead of stripping out the 2 on top, we strip out the 5 on the bottom? Let's see what that would do. So if I do n squared plus 2 over n to the 4th, would that change our inequality sign? What would our inequality sign be now? So our original has the bigger denominator.
Less than?
Yeah, so bigger denominator means it's less than. Okay, so maybe if we could figure out that if the green one is convergent, then the black one will also be convergent, right? So maybe we can just analyze this green one right here. Can we do something with this green series?
Take the limit.
If you take the limit, you'll get infinity over infinity, so we can't take the limit yet. I have an idea. Let's break it into 2 fractions. All right. Yeah. So let's analyze both of these. So this one here is just 1 over n squared. And this one here, if we factor out the 2, is 1 over n to the 4th, right? Can you see how both of these series are now in the form of a p series?
Yes.
Okay, great. So what can you say about both of these series?
They converge because the p
Yeah,
value is greater than 1.
yeah. So based on our slides, we can say this converges, and this one also converges. And then if you add 2 convergent series, that should still be convergent because it's finite plus finite, which is finite. So we just figured out that this converges. Okay? And then if this converges, what can we say about our original series? Yeah, so our original series is also convergent because it's less than something that's convergent. Okay, so comments regarding this question. I want to say that there are many different ways of doing this particular question that I'm sure you guys might have seen or thought about. But what I wanted to highlight was the process of using comparison test with the P series, okay? So that's why I specifically did it this way. So through manipulation, you want to get stuff in the form of 1 over n to some power. All right. Let me see what we have next. Okay, so here's the next example. You guys can try this on your own. So try to do it like the way that we just did the previous problem. See if you can get the answer. Okay, I'll give you 4 minutes. So yeah, just a reminder that there's many different ways of doing this. So if you can't do it the way we did the last question, see if you can do it another way. All right. Okay, so did everyone get an answer? Anyone need extra time?
I got it. I got it converges.
Converge. Okay.
I actually use something similar that you used on your last song.
All right. Let's go over it. You want to share your what you did?
Yeah, sure. So I thought of an equation that would have a greater value, right? Which is basically n squared by 4n cubed.
N squared 4n cubed. So this thing right here.
Yeah.
Okay. So you stripped out the -2. So if we compare these two, what would be your inequality?
The left one is greater.
So like this?
Yeah.
All right, let me just make sure that's right. So this one has the bigger denominator and bigger denominator. Oh no, this has a smaller denominator because it's -2. So if you have a smaller denominator, then you are large. Yeah, this looks good so far. Okay, so what you do after this?
I think I got the thing opposite. I think the function that I use has to be greater, right?
I mean, it depends. I mean, sometimes like you just continue and see if you can reach a conclusion.
The new function we made, like after simplifying it, you'd be left with 1/n, 1/4n.
Yeah, this is equal to um, 1/4n. Yeah,
And so like we know we could just take out the 4.
yeah, we could do that. So this is 1/4, and then we're left with 1/n inside. Okay. Yeah, this is in the form of P series now. So 1/n, what's that?
Convergent.
It's convergent? Let me double check.
Shouldn't it be divergent? Because it's equal to
Uh,
1.
Oh,
yeah, it's divergent. So if you look back at the slide, let me just paste the slide back here. So here's the P series thing. So if the exponent is less than or equal to 1, it's divergent. So this last part right here is divergent. I mean, that's fine. It's just whether or not we can reach a conclusion. So this is divergent. Our original series is greater than this one, right? So can you reach a conclusion based on that? So if we're greater than a divergent series, can you do you have a conclusion?
The conclusion should be it diverges.
Yeah, very good. So uh, this series diverges. Yeah, so we got it. Very good. So this is divergent, and we use the comparison test. So that's fine. Let me ask, did anyone do it a different way? Okay. Well, I want to comment that the only reason why we were able to reach a conclusion that it diverges is because we were greater than a divergent series. But if we happen to reach uh, a convergent series, then this would be the case where you would be inconclusive because being greater than a convergent series doesn't guarantee you to be anything. So the greater than sign was actually very helpful there. Anyways, there is actually another way to do this problem, and it's to use the integral test. So no one did that, right? Did anyone use the integral test? Okay, well, if you were to use the integral test, this would be integral of x squared over 4x to the third minus 2 dx. So I guess the only reason you would use it is because you would see that this integral is actually something we know how to do. So if you let u equals 4x to the third minus 2, then du is 12x squared. And if you have x squared here and you have x squared here, then this is actually doable. So the integral test was another option, but I guess this method we used over here is probably much simpler. Yeah, that's pretty much it. Anyone else have questions? I think someone had a comment. Is the summation sign pretty much the same as integration? That's a funny question. Yeah, I guess we can talk about that. So you guys might be wondering, well, what's the difference between summation and integration if they all have the same rules, right? I mean, the way we use summation is usually like for a series. So for a series, like your index are only whole numbers, right? So if you were to graph a series, like it basically looks like this. So it's like bars on the graph. So it's a summation of some series a to the n. And then if you were to integrate like a function, then this is sort of like it's like a curve instead. So it's like this. And in both of these expressions, like what you're doing is you're finding the area underneath the curve. Well, for the integral one you are. So this is area under the curve. But if you're dealing with a series, then that means you're just adding up a bunch of numbers. So what you're doing is you're just adding up all these bars here. So adding all the, I guess you call them rectangles. So series count for negative numbers. No, we never do series for negative numbers because for example, when we give you a sequence, usually your first instinct is to say this is the first term of the sequence. You never say like this is the negative fifth term of the sequence. So we don't really use negative numbers for series. Yeah, so like Riemann sum. But you can see how these two are very similar because you're essentially just adding up areas underneath some region, which is the explanation as to why a lot of the rules are the same. So I don't know if you guys can see it, but the symbol for summation and integration, you can maybe make them look very similar. So you start with summation, right, which looks like this. And then if you were to like sort of smooth it out, so like you write it a little bit sloppier, and then you go like this, and then you make it a little bit sloppier, and then you go like this, and then eventually, you'll get towards the integration sign. So I don't know what you guys think about that. Yeah, they're basically the same thing. All right, well, so that is all the stuff we had to do for today. Do try homework 8.3 in your free time. So this is the last section for the topics on exam 2. So I just want to take a moment to talk about exam 2. We have, how many more classes do we have before November 12th? We have November 5th and November 10th. Okay, so, all right. Yeah, we're ahead of schedule then because we're supposed to have one free lecture to say for like going over a review for the exam, but I guess we have 2 free lectures. So I'll probably have the review for exam 2 uploaded by either tomorrow or sometime Thursday before class. So I'll try to make it as early as possible so you guys can get a chance to see it before class on Thursday. But if I get it out to you really late, then we're probably not going to do much on Thursday. So Thursday and next Tuesday, those 2 classes before the test, I'll just dedicate both of those to just reviewing for the exam. So I'll send out a review sheet tomorrow or Thursday, and then you guys can take a look at it. We'll go through some of it on Thursday, and then if we still have more, we'll go through on Tuesday. And then Thursday will be the exam. Yeah, so I guess that's the plan. Do you guys have any suggestions besides that? If not, then that's what we'll do. All right. Okay, if that sounds good, then we'll stop here. I'll see you guys on Thursday. Have a good night, everyone.